Hello, our project is a progressive sampling method to optimize big data analyses. My name is Nihad Dababo,
And I'm Stephen Linsinger.
and our advisor for this project is Dr. Paraga Bagar for our senior project. For the agenda, we're going to start off with our problem statement, moving into our model building, and from there going into the process of our project and the challenges we'll face throughout this project. So for the problem statement, what is the optimal size of predictive models? When considering big data, it is easy to get caught up in the size and think that bigger is always better. But is that really a cost-effective approach? We must ask ourselves, how much is enough? Can we optimize the way we approach big data, and specifically in terms of regression analysis?
So, to put this problem statement into a visual, let us imagine a data set with n observations and x1 to xi explanatory variables, as seen here. To create a predictive model from a data set using multiple linear regression, we need to first select the explanatory variables that will best predict the response variable. At first, with small numbers of observations, chosen randomly from the much larger data set, we find that the variables selected for the model aren't always the same. This can be due to a variety of reasons, but a large factor is variability in the data. Let's call it turbulence or instability. As we increase the number of observations chosen for building the model, we see the variable selection become more consistent. We reach the min when we have consistency in the variables selected for the model. Now that we have our variables selected, we go through the rest of the model building process to build a predictive model that meets the model assumptions, linearity, equivariance, normality, and thus can be relied on for predictions. As the number of observations used in the model building process increases, we expect the accuracy of the model to increase as well. We reach the max when the accuracy of the model is no longer getting increasingly better with more observations used to create the model. So, between the min for consistent variable selection and the max for diminishing returns of accuracy, we find ourselves looking at the optimal zone. It is here where we will find the answer to our problem statement of what is the optimal size of predictive model. Variable selection. The big question at hand in variable selection is, what variables have the strongest association with the response variable? One can look at scatter plots or added variable plots. However, our modern day software, JMP, Minitab, etc., can effectively and efficiently recommend variables for the model. With the large amounts of available variables in big data, there are an even larger amount of models that can be created from any number of the available variables. Variable selection techniques offer a way to explore some, but not all, of the possible models. Some examples include forward selection, which adds variables one by one to the model until no further addition significantly improves the fit, or backwards eliminations that starts with all the variables in the model and removes them one by one, the variable making the smallest contribution. And then stepwise is actually a combination of both. It adds a variable to the model, removes the one making the least contribution, and it's an iterative process that continues until the best model is found, or a good model is found.
After the variables have been selected, we must then check if the assumptions are met. The assumptions of multiple linear regression are linearity, equivariance, and normality. If the assumptions are not met, then we can explore various transformations to help our model meet the assumptions. Transformations can take many forms. Some of the common ones are shown here. Making transformations is often an iterative process where many different things will be tried separately and together, and often a combined solution of transformations will lead us to meet the model assumption. Once we have verified the model assumptions, we can move on to progressive sampling. Progressive sampling is the method of progressively increasing the sample size until model accuracy is maintained. A case study by F.J. Provost, D. Jensen, and T. Oates, called Efficient Progressive Sampling, found that subsampling the data gave the same accuracy as the entire data set at much lower computational cost. This is fundamental to our research, and through progressive sampling, we will look to identify the point at which we see diminishing return and the accuracy of the model. We believe that at a certain point, The law of diminishing returns takes effect in relation to model accuracy. This will be observed in a graph similar to the one in front of you, where the accuracy will begin to flatline after a certain number of observations is reached. Thus, any more observations would not be giving an increasing return in model accuracy. Once the point is reached, it's no longer cost effective to continually increase the number of observations analyzed. We will progressively sample our data sets starting with 50 observations and then 100, 250, 500, 750, 1000, 2000, etc. The scaling of the progressive sampling will be determined by the total size of the available data set as well as the turbulence observed. Graphs will be made, like the one above, to track the accuracy of the model as the number of observations is increased. Accuracy measures such as R-squared adjusted, press, standard error of the estimate, and much more will be used to plot against the number of observations.
R-squared adjusted is a way to measure the amount of variability explained by the model while also taking into account the number of variables in the model. S, which stands for standard error of the estimate, is basically the average of how wrong your model is. Now that we've outlined the methods of analysis and the measures of accuracy by which we will look for diminishing returns, we must look to streamline our methods for efficiency purposes. We are currently exploring options of integrating JMP with SAS. Our ideal method would use SAS code to automate progressive sampling after the variables have been chosen and the required transformations have been made. In this scenario, SAS would also automate the collection of the model accuracy measures. In addition, SAS has the potential to report to Excel, and if all these features are utilized, then an extremely efficient process can be created to carry out the repetitive analyses tasks in this project. In addition to streamlining the repetitive tasks, the process of finding the optimal zone must be repeated for many datasets. These datasets must vary in number of variables available, strength of the variables available, the variability within the dataset, and the number of observations. We must carry out our methods on varying datasets so that we can better understand the driving factors that determine the optimal size of predictive models. Thank you for watching our video presentation today. If you have any questions or comments, feel free to reach us at our emails located here.